paper, Tita. Leonardo, if you could please load the video so that we can start on time. Okay, thanks. So this paper will be presented by João Pedro Klock and Jonathan Correa from Concert Technologies in Belo Horizonte. And it's entitled A New Automated Energy Meter Fraud Detection System Based on Artificial Intelligence. So on my clock, it's 8:30 sharp. So please, Leonardo, you can hit play. Thanks.
Hi, my name is João Pedro Klock, and with Jonathan Mota, we will present the work, A New Automated Energy Meter Fraud Detection System Based on Artificial Intelligence. This work is divided in the following sections: an introduction to the subject, a description of our work, the proposed system architecture, the results section, a conclusion, and the acknowledgements for this work. Electrical energy is nowadays a basic need for almost all of our society, including vital necessities, and therefore the correct operation of the electric power system is of extreme importance. The electric power system is susceptible to two kinds of losses: technical and non-technical losses. Technical losses refer to the physical limitations of the elements of the electric system, while non-technical losses are related to human actions, such as mistakes on billing consumptions or fraud in energy meters. Even though many resources are spent in fraud detection, it's still very hard for electrical companies to find some disguised frauds that are difficult for the field inspectors to detect, with some types of frauds being only detectable in a laboratory with proper equipment, which may take a long time and cost a lot for the companies. There are two types of fraud detection methodologies: hardware and non-hardware based solutions. Regarding the non-hardware based solutions, most of the previous solutions use energy meter. Regarding the non-hardware based solutions, most of the previous solutions use energy measurements or the consumer profile to predict the behavior of an energy theft consumer. But because they use historical data, these solutions cannot be applied directly in field inspections. As for the hardware-based solutions, most works require data acquisition for posterior calculation or processing, which may not be available at the time of the inspection. Finally, regarding the field inspections, even though some works provide a useful inspection guideline, it's still challenging to perform a correct and reliable field inspection within a plausible time. Therefore, in order to deal with these problems, mainly focused in field inspections, in this work we propose a set of applications based in artificial intelligence that combines both hardware and non-hardware approaches in order to ensure a correct inspection. Both solutions are combined in a mobile application that is easy to use and suitable for field inspections. For the hardware solution, previous works have used a time domain reflectometry technique to characterize an impedance profile of conductors or devices. We applied this technique to build a profile for energy meters and build an artificial neural network to classify its impedance, so that we can identify problems in the energy meter. We also use a convolutional neural network module where we are able to take pictures and detect visual irregularities in energy meters. Previous works in this field have used CNNs to perform the automatic reading of meters, but not for fraud detection. Finally, our complete methodology is capable of automatically detecting irregularities and can be entirely performed in a field inspection. We start by showing our proposed system architecture. It is composed of two main modules: a visual irregularity detection module, which contains the CNN information, and an impedance irregularity detection module, which contains the ANN, and that is used in combination with an embedded application and a TDR. A mobile application unites both modules and contains the processing functions for the first module, and communicates with the embedded application through Bluetooth in order to acquire the second module data.
The module to analyze internal impedance consists in a custom hardware based in a SOC FPGA, more specifically a Xilinx Zinc 7000 integrated with a high-speed analog to digital converter and a high-speed digital to analog converter and a Bluetooth module to communicate to the mobile application. The FPGA integration with the high-speed converters, when synchronized, can act as a TDR, and with the result of this application, we apply an artificial neural network to determine if exists evidence of tampering the energy meter. The neural network is accelerated with a software hardware co-design using the FPGA within the system.
For the visual irregularities analysis, two networks and datasets are proposed, one for energy meters and one for their tags, and this table shows the amount of units for each class in dataset. For the energy meter dataset, there are 7 irregularities: tag absence, lead absence, damaged lead, including holes or broken lead, dirty lead, or a lead with too much dirt, or even with insects that becomes hard to read, damaged plate or register, when one of them or both is crumpled, electronic meter turned off or defective, and terminal problems, which includes a jumper between phases or the terminal lead broken. As for the tag dataset, there are 2 irregularities: tag absence and broken tag, when the tag is cut or ruptured. The proposed network is divided in 3 main steps: an input layer, the network layers itself, which basically consists of the feature extraction layer, and an output layer. The input layer begins with the input data. The data is divided in train, validation, and test sets. Due to the unbalanced distribution between classes, the training set goes through an oversampling process, and then through a data augmentation process, where small transformations are performed, such as rotations, scale changes, and horizontal flips. The network layers consist of a feature extraction network with its proper preprocessing step, an average pooling layer to concatenate the outputs, a dropout layer to improve regularization, and finally a prediction layer. During training, the feature extraction network layers will be first frozen and then unfrozen for fine-tuning. Finally, in the output step, the network output is mapped to a list of irregularities.
The mobile application was developed in Flutter for Android devices and is intended to control both modules in a single interface. It uses the cell phone camera to apply the visual irregularities detection and controls the internal impedance module through Bluetooth communications. At the end of the inspection, a report is generated with the relevant information to the user, and can be. As the original prototype was not ready at the moment of the development of this work, the data was obtained in lab utilizing a signal generator and an oscilloscope to simulate the TDR function. With this data, the artificial neural network was trained within a host computer, and the results are shown in the table. All samples related to tempered matters had high errors in classification and can be selected with a simple post-processing with software, determining a threshold like 5%, for example. An important fact is that some of the tests were done by the load side of the meter, and this had high error rates, so this isn't the most suitable way to use this system. To access how much the co-design could accelerate the solution, the execution times were measured in a software implementation and a hardware-software co-design implementation. We can see that the co-design implementation is at least 35% faster than the software solution. Thinking a hardware acceleration of the ANN with the FPGA, 6 different implementations were done, merging parallel and sequential implementations of the algorithm. This implementation was done using high-level synthesis that converted a high-level code first implemented in C language to a hardware description language, more specifically the VHDL. This was done to analyze how much the architecture of the code impacts in the acceleration achieved with the FPGA implementation. There is a clear trade-off between latency and resource utilization. To compare with the pure software solution, the best solution achievable with the resources available can be up to 89% or faster.
Since there are no other methodologies to be compared that performed visual irregularity tracking in image meters, the CNN results includes a search for the ideal parameters for the proposed network. Since the classes or irregularities are not mutually exclusive, that is, meters can have more than one irregularity, we used the binary cross-entropy loss, and since approaches such as accuracy may lead to a high number of zeros, used the F1 score as our evaluation metric. Both the loss and the F1 score will be used to test the models. We divided the datasets in 70% for training and 15% for validation and test each. In our test, we compared the learning rate, the feature extraction network, the dropout parameters, the input image size, and the amount of unfrozen layers in the fine-tuning part of the training. The tests were performed in the meter network, and since the results were similar for the tag network, we omitted the tag results. For the learning rate comparison, we tested 5 different values. According to the plot of both the validation F1 score and the validation loss, the one with the smoothest transition is 10 to the minus 6, and this was chosen as our learning rate. For the feature extraction network comparison, we tested 5 networks. The table shows that the network that was able to achieve both the lowest loss and highest F1 values was the exception network, and this was chosen as our feature extraction network. For the dropout parameters comparison, 5 values were tested. Results show that even though more than one achieved the same F1 score, the one with the lowest loss was chosen, which is 30%. For the input image size, 4 values were tested. The 299 size, which is the default for the exception network, achieved a high F1 score and a good loss, so we chose this size. Finally, for the amount of unfrozen layers during the fine-tuning comparison, we tested 5 values, with 132 being the total number of layers in the network. Since every number achieved almost the same performance, we decided to analyze the number of epochs taken to achieve convergence, and thus we chose to fine-tune all layers. Finally, for the conclusion, in this work we proposed an artificial intelligence joint solution combining both a TDR-INN hardware solution and a CNN software solution. The TDR-INN solution was able to identify tempered meters with a good accuracy, and the co-design solution was able to provide a good improvement in latency. Future works include optimizations in the code and RTL-level implementations to accelerate the processing time. As for the CNN, the solution is capable of detecting visual irregularities, but the lack of images, which resulted in unbalanced datasets, affected the results, achieving a highest F1 score of around 67%. Since the majority of the irregularities are in the classes with most images, the network was still able to maintain a reasonable performance in field inspections. Future works include acquiring more images, mostly for the unbalanced classes, and also varying more parameters. Finally, this work proposed novel applications of fraud detection, allowing a faster and more reliable inspection. We would like to thank CPFE and Consage for the technical and financial support in this work. Here is our contact information, and thank you.
Thank you, João and Jonathan, for the presentation. I would like to start asking if there are any questions from the audience. Okay, so maybe while the audience thinks about it, I'll have a few questions. First, regarding the impedance irregularity detection module, what kind of frauds is it trying to detect? I mean, what are the changes that people usually do on these meters, and that this particular property can be used to detect them? Is it any kind of fraud? Is it a specific subset of all possible frauds? How is this information obtained by you when modeling them?
Good morning. Regarding to this module, we mostly want to find hardware modifications like bypass of the energy measuring unit and some uh, resistors broken and this kind of modification that could influence on the energy measuring
Hmm.
activity. No, it's not activity, but the act of the meter to measure. We want to try to find a way of determine this just by creating a impedance profile of the energy meter.
Hmm. And these changes, are they necessarily caused by fraud, or is it possible that some natural failure due to wear out will also cause some kind of these changes in impedance?
Well, we don't. I can't say with 100% sure, but I think that with an old meter, for example, can have some
Hmm.
natural natural. Sorry, I forgot.
Failure.
Yeah, some not natural failure with
Hmm.
with some time. And
Hmm.
in this case, we also will have a problem in energy measuring. So we want to find this type of failure too
Hmm.
by classifying the
Yeah,
impedance.
yeah, of course. So, and regarding the latencies that you have reported some latency numbers regarding the neural networks that you have used. Um, and these are very low numbers. I mean, they're very fast neural networks. Do you guys have some kind of real-time constraint that forces you to have such low latencies? Or maybe if a lower cost solution could be found, even if with a higher inference latency, if that would also be acceptable?
Well, one question that it was a surprise for us that was this case of latencies to find this. We used a artificial neural network that we converted to C language, and the execution was really fast to us.
Hmm.
Maybe to use some sorry you told about
If we had a lower cost solution that
uh,
had a longer latency, if that would also be usable by technicians in the field, or
all right. The question is to achieve our solution, we would need a FPGA to make the
mm,
interface with the high speed ADC and DAC
I see.
to achieve. So one of the first steps to the solution was to find a hardware that could do this interface, and we found that Xilinx Zinc 7000 was the cost benefit best solution for this. So maybe
Okay.
I we could have a SoC
Hmm.
slower as SoC, but we would not have a FPGA with the same cost and same benefit.
Okay.
So yeah, the I don't know if we can lower the cost to have more latency because of the interface.
Okay, I see. Yeah, that makes sense. Okay, thank you. If we don't have any questions from the audience, we can proceed to the next paper, which is entitled Machine Learning for Identification and Classification of Crops and Weeds, and it will be presented by David Armstrong from the Federal University of Rio Grande do Sul and the Instituto Senai de Inovação em Metal Mecânica. So let's hear from David.
Hello, my name is David Armstrong. I'm going to be presenting our project on machine learning for the identification and classification of crops and weeds. written in conjunction with Dr. Marcelo Goetz from the University of the Rio Grande do Sul, Dr. Vitor Nardelli and Dr. Victor Gomes from the Instituto Senai de Inovação in São Leopoldo. First of all, a quick overview of our project. Initially, we'll start with the problem definition, followed by the system requirements. Next, we'll go on to our proposed solution, followed by how we implemented our solution, a few tests on embedded systems, the results we came to, and finally our conclusions. First of all then, the problem definition. As we know, in recent years there has been a constant demand for higher productivity in agriculture, given the continuous growth of world population. Until recently, the solution for this sort of issue was quite simple. A new fertilizer could be developed, a new pesticide could be developed, and these could be applied to an entire field of crops. However, in recent years, with greater environmental pressure and more health concerns around these kinds of products, farmers have increasingly turned to technology to try to solve these issues. This includes aerial photography and remote sensing systems, and in our case we're developing a small robotic vehicle for the identification of crops and differentiation of crops and weeds, and which then can be used for the removal of the weeds to increase productivity. Going on then to the system requirements. In order to be better than existing solution of simply spraying an entire field with pesticides, obviously the system must be targeted. In addition, it must be an autonomous system. Now, why is that? Very simply, the distances involved in agriculture are much greater than, for example, in a typical industrial setting. And unlike an industrial setting, getting connectivity to a robotic vehicle in the field is generally quite difficult. As such, it is extremely difficult for a robotic vehicle to be controlled from a central system, and as such the robotic vehicle should be capable of performing detection and classification autonomously. This then would result in replicating the human experience of being able to differentiate between crops and weeds. Our proposed solution then involves creating an object detection system using artificial intelligence. Now, why use artificial intelligence for this problem? Well, really, it is extremely difficult to define a weed in a way that can be understood by a computer. After all, both the crop that you want to keep and the weed that you want to remove are fairly similar. Both are green, both have leaves. It's very difficult to define a rule that can be used to differentiate between the two. As such, an approach using artificial intelligence can solve this problem by using human experience to manually label the different crops and weeds, and then training a system to identify these classes. In addition, to satisfy the other requirement, the system must be implemented on an embedded system. So, our proposed solution regarding the object detection. There are essentially two families of object detection frameworks. The first is YOLO, which is a high-speed system. However, it generally has lower accuracy than other solutions. The other possibility then that we studied is the regions-based convolutional neural network, and while this solution is slower, it gets state-of-the-art accuracy. So in terms of our regions-based convolutional neural network, a convolutional neural network is a neural network that is applied using a convolution to an input image. In the case of the RCNN, it is a two-step architecture where the first step is responsible for finding the broad location of an object, and the second step is responsible for performing the classification. There have been various advances to this architecture since it was first proposed. First is the fast RCNN, followed by the one we are using, which is the faster RCNN. This model uses a convolutional neural network for both steps, so both for classification and detection, and these layers are shared between the two steps to speed up the system. This shared layer is called a backbone, and one of the advantages of this system is that it can use a backbone from a common object classification system such as VGG16 or ResNet50, which is what we have used. In terms of embedded systems then, traditionally an embedded system was a dedicated processor capable of performing a single task or a single application, and as such it had relatively limited processing capacity. However, in order to run an algorithm like faster RCNN, a dedicated process like this is insufficient, and as such we turned to using microcomputers to perform our inference. In terms of microcomputers, there are various possibilities. What we chose was the Raspberry Pi 4, since this is a low-cost solution and it achieves relatively good performance on its CPU. In terms of our implementation then, we used the Python programming language along with the Detectron2 image classification, image processing library, and the reason for this is because it's a high performance library since it's already implemented in the PyTorch framework, which is a fast machine learning framework developed by Facebook. In terms of the dataset that we used the CWFID dataset, which consists of 60 images and approximately 500 annotations. Our reason for choosing this dataset was primarily due to the quality of the annotations. So, unlike many other datasets we found, this one contains extremely high quality detailed annotations, and we discovered that this really is far more important than the number of images. In order to get around the issue of having few images, 60 images really is quite few for an object detection application, we used significant augmentation on our images, principally around cropping the images up to 10% and randomly flipping our images to provide new views of our data. Going on then to our tests in embedded systems. Our training consisted of 20,000 iterations on an NVIDIA M5000 GPU. Our results then for the localization phase were a precision of 82%, a recall of 90%. You can see the confusion matrix in the top right hand corner. And then for our classification phase, we got a precision of 91% and recall metric of 100% over the dataset that was tested. This then, with our preliminary results defined, we could go on to studying the time taken to perform the inference. Obviously on a high-powered GPU this was relatively fast, coming in at just under 0.2 seconds. However, on the embedded system, our Raspberry Pi 4, the detection took a lot longer at just under 43 seconds. Moving on then to our improvements, we enabled just-in-time compiling on the PyTorch library in order to improve performance, and in addition we enabled parallel processing on the Raspberry Pi 4, which has a quad-core CPU. We also tried modifying our backbone depth to see what effect this would have both on speed and on accuracy. However, we discovered that this is quite unpredictable, so we moved on to simply adjusting our image resolution. Obviously this follows a relatively quadratic curve, so here we can see the prediction time in black, and the top graph shows the localization precision and recall. The bottom graph shows the classification precision and recall, and the time down the right axis. you can see that around the 800 pixel mark, so that's 800 by 600, we hit the maximum for the classification, and we're getting relatively good results in the localization phase as well for a relatively low prediction time. We decided therefore to use this to compile our results. So our final configuration then is using the ResNet 50 backbone. That means the backbone using 50 layers. We used 800 by 600 pixel resolution images, and we trained this for 30,000 iterations, unlike our previous attempt at 20,000. The inference then took 12.8 seconds on the Raspberry Pi 4, and we got a localization precision recall of 84 and 89%, and a classification precision recall of 96%. Here you can see some visual representation of our results. So in general, classifications were relatively good. You can see that it missed detection here, and down at the bottom it has mistakenly classified some crops as weeds. Finally then, our conclusions regarding the platform that we used, the Raspberry Pi 4. This platform would be a relatively good option for low velocity applications, and since a lot of projects, both in agriculture and otherwise, use a Raspberry Pi 4, this project gives a good baseline for any of those trying to use the faster RCNN architecture. In addition, there is the prospect of future improvements on the Raspberry Pi 4, so this current generation has improved its performance significantly when compared to previous generations. Regarding then the faster RCNN, one of the principal advantages of this architecture, in addition to being getting extremely high accuracy for object detection, is the easy trade-off between speed and accuracy. So depending on the application, a more time-sensitive application can easily reduce the resolution and get fairly predictable results from that, or simplify the backbone. So, thank you very much.
Thank you, David, for your presentation. Do we have questions from the audience? Okay, so we have a question from the audience. So Flavia Maristella asks, you have achieved good results in terms of precision. What improves do you believe it can be done to improve the training with good accuracy?
In
terms of time.
The issue with trying to improve the precision and so on is that it really is a definite trade-off between the time taken and the accuracy of the results. Some improvements that could be done are, for example, looking at the other network that I mentioned, the YOLO network. It can get better, it can get higher speed results. The question is then, is the trade-off with accuracy in that case worth it? Certain other things that could be tried probably would be using a larger data set with a smaller images, so that we get the advantage of more data, but lower resolution images get us faster results. I mentioned that the backbone is another factor to be taken into account. The problem with the backbone that we found was that it tends to be quite unpredictable, unlike the nice quadratic curve of changing the resolution. Changing the backbone can move about an awful lot, and it's quite difficult to see. But if you really needed the high performance on that architecture, changing the backbone to something simpler might work.
Okay. Do we have other questions? In the meantime, I have a question. What kind of crops and weeds are available in the data set that you have used? And do you think these conclusions can be generalized to different kinds of crops? I assume that training would have to be redone for each different kind of crop and weed because things are different. But do you consider that this particular data set provided a hard to distinguish example or a particularly, I don't know, maybe an easy to distinguish example? Do you have any thoughts on that?
I think the crops used were carrot crops.
Mm-hmm.
Yes, I think that if you were to use it with different kind of crops, you would have to retrain the network, or else, of course, if you had a data set that covered multiple different types, there might be a chance there, but I think that would be extremely difficult to be able to correctly differentiate that. In terms of the difficulty of identifying the crops versus the weeds in this case, I would say it wasn't particularly easy in the sense that both plants, both images look fairly similar. For example, if you in the paper, figure 1 shows a specific example of crops and a weed, and the weed really looks fairly similar to a carrot plant. So it's a fairly difficult data set, but yeah.
Okay. And the idea of this neural network would be to perform some kind of diagnosis, like to measure the amount of weeds in a given field, or do you think it could be used to take some kind of countermeasures, such as I don't know, chopping down the weeds and leaving only the good crops?
Yes, there are certain applications already that involve chopping down weeds. A lot of them involve a much larger sort of platform and involve communication with a base station and that sort of thing. Mm-hmm. Yes, the idea would be to use this as some form of, or advance this into some system that would be able to remove weeds. Whether that would be by chopping or removing the weeds mechanically, or simply spraying the individual weeds with pesticide rather than blanketing the whole field, which is already a large improvement.
Yeah. Okay. So if we do not have any questions, I would like to once again thank David for his presentation, and we can move on to the next paper. Thank you, David.
Okay, thank you very much.
So the next paper is entitled Assisted Counterexample Guided Inductive Optimization for Robot Path Planning, and it will be presented by Mengtse Li from the University of Manchester.
Hello, this is Mengtse Li. Welcome to the presentation of our paper, Assisted Counterexample Guided Inductive Optimization for Robot Path Planning. The presentation is divided into following 5 parts: background knowledge, objectives, ACGL-based path planning algorithm, experimental evaluation, conclusion, and fieldwork. So let's start with some background knowledge. Let me introduce how CGL and optimization technique works. Starting with define decision variable x and cost function fx, we define the constraints with assumed directive, which is x in bounds, fx new smaller than fx current. Fx current is a current cost function value, and fx new is a smaller cost function value we would like to generate. Then we define the property with assert directive, fx new larger than fx current, and we pass them to the verification tool. If the verification fails, which means a smaller cost function value is found, so we update x and fx current with fx new. Then we go back to start another iteration to find smaller cost function values. And if the verification succeeds, we need to check if the precision p reaches the upper bound. If it didn't, so we need to update the p and go back to start another iteration. If it reaches the upper bound, so we need to end with the current result. Path planning can be considered as an optimization problem, so CGL can be applied to achieve the optimal path by iteratively requesting counterexamples from SAD or SMD solvers. Here is an example of applying CGL algorithm to solve a path planning problem. The aim is to figure out a path which has shortest distance from starting point S to target point T, avoiding all obstacles. After first iteration, the blue path is generated by CGL, and a green path with smaller cost function value, which means with shorter distance, is generated after the second iteration. So, optimal paths can be generated after massive iterations. However, CGL-based path planning algorithm requires large execution time, and requesting counterexamples from SAD or SMD solvers is the most time-consuming process. So in order to improve the efficiency, we propose a novel path planning algorithm based on ACGL. ACGL combines CGL with an accelerate algorithm, which relies on CGL to preserve the optimization ability and relies on the selected accelerate algorithm to improve the efficiency. So in this work, gradient descent is selected. Here is an example explaining why ACGL is more efficient than CGL. Assume we have a cost function fx, so on the left is updated by CGL. Starting from the initial position, it updates optimal candidate only by requesting counterexamples. And as for ACGL, starting from the initial position with requesting counterexample once, then gradient descent is applied until it trapped in a local minimum. So at this moment, counterexample is employed again to generate a smaller cost function value, and the gradient descent is applied to update the optimal candidate to the global minimum. The optimization process of employing ACGL contains fewer times of requesting counterexamples, and the gradient descent, which is much faster, is applied instead. This is why ACGL is more efficient than CGL. Next, let me introduce objectives. We have three objectives. Firstly, develop an ACGL algorithm with gradient descent as an accelerate algorithm to generate optimal paths. Secondly, evaluate the proposed ACGL-based path planning algorithm. Thirdly, compare the results with other traditional optimization techniques-based path planning algorithm. Overall, the main object of this work is to propose and evaluate a novel offline mobile robot path planning algorithm based on assisted counterexample guided inductive optimization algorithm. In order to achieve ACGL-based path planning algorithm, there are two steps of applying ACGL to path planning problems. Step 1. Formulate the path planning problem as an optimization problem. Define decision variables, cost function, and set constraints. Step 2. Apply ACGL to find an optimal path that minimizes the cost function and satisfies the constraints. Let's start with path planning problem formulation. Path planning is to find the valid optimal path from a starting position to the desired position that avoids all possible obstacles in the motion space. The optimal path consists of a sequence of points consecutively and sequentially connected by strict segments. Here is an example. We can define a starting position S as P1 and the target position T as Pn, and define the points consisting of the path as L, which contains P1, P2 to Pn, and the cost function can be defined as this. The cost function JL is the length of the path, and N is the number of points on the desired path. Then we define the obstacles and the environment limits. So the optimization problem for path planning can be written as this. To minimize the cost function JL, wherever points on the path is within the environment limits, but cannot be within the obstacles. Before applying ACGL to path planning problem, let's go review the CGL-based path planning algorithm. In CGL-based path planning algorithm, directive assume is used for modeling the constraint set, like obstacles and the environment limits. Also, assume is used to set a constraint GLI smaller than GLI minus 1, which means the new generated cost function value must be smaller than the current cost function value. And the directive set is used for holding a global optimization condition, which is GLI larger than GLI minus 1. So we need to verify the satisfiability of G optimal. Then, if the verification fails, which means a smaller cost function value is found, optimal candidate GL is updated if a smaller cost function value is generated from a counterexample. And variable P is used to control the precision and discretize the state space. Starting with number of points n equals to 1 and precision variable P equals to 1, after maximum time of iterations, optimal paths can be generated. Now let me introduce ACGL-based path planning algorithm. It is quite similar to the CGL-based path planning algorithm, but it takes an additional input, that is gradient descent function GL. ACGL additionally employs gradient descent to calculate optimal candidates iteratively. Similar to CGL-based path planning algorithm, we use assume directive to define GLI smaller than GLI minus 1, and we use a assert directive to define the optimization condition. And it requires counterexamples once. If smaller cost function value is generated, we pass them to the gradient descent function. Gradient descent function is employed to update the optimal candidates. So new optimal candidates are generated either by extracting from counterexamples or by applying gradient descent. This is how ACGL-based path planning algorithm works. Now let's move on to the experimental evaluation. There are 3 experimental goals. First one is effectiveness, to evaluate the effectiveness of the ACGL-based path planning algorithm. And the second one is efficiency, to compare with CGL-based path planning algorithm. And the third one is to compare with other state-of-the-art approaches. So in this work, PSO-based path planning algorithm and GA-based path planning algorithm is selected. And here is the experimental setup. Tools for executing CGL-based path planning algorithm and ACGL-based path planning algorithm are as follows. ESBMC is selected as a model checker, and Bolector is selected as a SMT solver. And as for executing GA-based path planning algorithm and PSO-based path planning algorithm, MATLAB is selected. As for the experimental environment settings, motion space is modeled as square, obstacles are modeled as blue circles, safety margin is represented by red circles. Here are 2 experimental environment settings. The first one, the setting 1, it has 1 obstacles, and as for setting 2, it has 4 obstacles. Point S is the starting point and the point T is the target point. So the aim is to generate the valid optimal path from S to T, avoiding all obstacles. In order to answer the first 2 experimental goals, which is efficiency and effectiveness, we need to evaluate CGL-based path planning algorithm and ACGL-based path planning algorithm in setting 1 and setting 2. So set the maximum execution time to 2 days. Here are the results. Red paths are generated by CGL-based path planning algorithm, and the blue dotted paths are generated by ACGL-based path planning algorithm. As we can see, ACGL-based path planning algorithm can generate paths extremely close to the global optimal path and solve the optimal path planning problem. So the first experimental goal, effectiveness, is achieved. In order to identify the second experimental goal, efficiency, we need to compare CGL-based path planning algorithm with ACGL-based path planning algorithm. So we plot the reduction trend of the cost function values for setting 1 and setting 2. The horizontal axis represents the times of optimizing the path planning problem, and the cost function values are shown in the vertical axis. As we can see, the blue line represents the ACGL best path planning algorithm, and the red line represents the CGL best path planning algorithm. For both setting 1 and setting 2, the blue line is below the red line, which means with the same execution time, the ACGL best path planning algorithm can always generate a smaller cost function values if compared to CGL best path planning algorithm. So ACGL best path planning algorithm generates passes closer to the global optimality with less execution time. So the second experimental goal, efficiency, is achieved. In order to identify the experimental goal 3, comparing with other state-of-the-art approaches, so GA-based path planning algorithm and PSO-based path planning algorithm are selected. Firstly, let me introduce experimental results of applying GA-based path planning algorithm in both setting 1 and setting 2. Here, for each environment setting, it contains 3 n equals to 4 cases, and 3 n equals to 5 cases, and 3 n equal to 6 cases. The execution speed of using GA for solving the path planning problem is extremely fast. Each experiment was completed in a few minutes. However, as we can see, the passes generated by GA-based path planning algorithm are further from the global optimality if compared to the passes which are generated by ACGL-based path planning algorithm. And there is uncertainty that the cost function value converges differently, and sometimes even fails to converge to a global optimality. So if compared to GA-based path planning algorithm, ACGL-based path planning algorithm is more stable and reliable. Then, as for evaluating PSO-based path planning algorithm in both setting 1 and setting 2, here are the results. For each setting, it has 2 kinds of results. Passes generated by the algorithm with appropriate parameters, and the passes generated by the algorithm with inappropriate parameters. And for both appropriate parameters and the inappropriate parameters, we got a n equals to 4 case, and the n equals to 6 case, and the n equals to 10 case. With appropriate parameters, like number of particles, acceleration coefficients, neighborhood size are set to the appropriate values, we can get the passes which are really close to the global optimality. So the cost function value always converges to the global optimality if the parameters are set to the appropriate values. So PSO-based path planning algorithm with appropriate parameter is fast, stable, and reliable. Here is the overall results to answer experimental goal 3. GA-based path planning algorithm is faster, while ACGL-based path planning algorithm is more effective and more stable. PSO-based path planning algorithm is stable, fast, and reliable, but not easy to tune the parameters. However, ACGL-based path planning algorithm is much easier to tune. And here is a conclusion and future work. We presented a novel mobile robot path planning algorithm, which relies on the ACGL algorithm to solve the optimal path planning problem. And the proposed algorithm can generate optimal passes with significantly shorter execution time than the original CGL-based path planning algorithm. And compared to other state-of-the-art algorithm, it is slow, but it is stable, reliable, and more robust. And as for the future work, develop other accelerate algorithms to assist CGL and explore the best accelerate algorithm for CGL to solve the optimal path planning problems. That's basically everything about our paper. Thanks for listening.
Thank you, Mense, for the presentation. Do we have questions? Well, I have a question. You compared the algorithm you have proposed. You have compared it with genetic algorithms, and you have mentioned that generic algorithms had a much shorter running time.
Yes.
But they failed to reach the same quality of the solutions that were found. But generic algorithms can be tuned in terms of population size and number of generations to control the trade-off between execution time and the quality of solutions. And my question is, have you considered tuning your generic algorithm so that it would have an execution time comparable to ACGO to see if it still, if it still provides inferior results compared to your approach?
Yes, I'm trying to control the until the chromosome, like the point, like with more chromosome, like more points in the path, so the path generated is more further from the global optimality, but it's generally good. And when I try to tune the parameters, so if I don't tune the parameters, the result will be really far from the global optimality.
Okay. And this ACGO approach that you have developed, have you considered applying it to other optimization problems other than path planning?
Sorry?
Have you considered applying the ACGO approach that you have developed? Is it applicable to other optimization problems other than path planning?
Because this work is built on a student from the University of Manchester, so I mentioned it in my paper. So his contribution is to apply the ACGO technique to optimize other cost functions, like to apply our situations. So he provided a result which is ACGO has the same ability as a CGL technique and without limit the application range.
Okay. We have a question from the audience, from Leandro Becker, and he asks if it is possible to use the proposed solution to compute path planning online if obstacles are detected on the flight.
Yes, so basically, it is so far the execution time is still a bit large. So you can see from the result, it takes about like 16 hours to generate a optimal path, but because the cost function is smaller, so the gradient will not be implied as many times when it starts. So the conic example is applied again. So the time-consuming process is still there, and if we can develop more efficient accelerator algorithm in the future, so it could be realized.
Okay. Do we have any other questions? No? Not then. Again, thank you, Mense Lee, for your presentation.
Thank you.
And we move on to the next paper, which is entitled An Optimization Approach for Emergency Vehicle Dispatching and Traffic Lights Adjustments in Response to Emergencies in Smart Cities. And it will be presented by Elivelton Rangel from the Federal University of Bahia.
Hello everyone, my name is Elivelton and I will present the paper An Optimization Approach for Emergency Vehicle Dispatching and Traffic Light Adjustments in Response to Emergency in Smart Cities. This paper was written by me, Daniel Costa, and Michael Peixoto. Now, I will do the outline presentation. First, the introduction about the problem context. Next, I will present the context scenario. After it, the proposed approach will be presented. And next, the simulation results with our methodology will be shown. And finally, I will conclude this presentation. The adoption of sensors-based monitoring approach has opened up a range of possibilities for data recovery, distributed process, and quality evaluations in urban scenarios. Efficient management systems provide a fundamental service for modern cities, exploiting different sensing processing technologies for the real-time handling of critical situations. Traffic jam, traffic accidents, fire outbreak, urgent patient transport, violence protests are some possibilities can be monitored by sensors. A study done in 2016 showed that approximately 40% of inhabitants of São Paulo, Brazil, spend an average of 2 hours commuting. This time sets in motion a series of critical social and economic events for these cities. The causal disorders produced a high estimated economic loss, representing about 7.5% of the city's GDP, gross domestic product. But financial disruption is not the only critical factor related to urban mobility challenges. Particular motor vehicles are responsible for emission of 60% of CO2 in the transport sector, potentially contributing to the ongoing global warming. And reducing this one is one of the main goals of the United Nations Organization by 2030. Traffic accidents is a particular problem that deserves a lot of attention in urban scenarios. According to World Health Organization, this type of accident is the 80th largest cause of death in the world in 2016. Projections show that in 2030, it will be the 10th largest cause of death worldwide. The Internet of Things paradigm, the vehicular ad hoc network, and intelligent transport system are some of various technologies that can assist in solving environmental problems. The efficient combination of these approaches can be essential to reduce or even mitigate some related urban context problems. Now we have the goals of this project. The first one was developing an algorithm for automatic assignment of emergency vehicles to incident site. When an incident happens, an emergency alert system detects, processes, and transmits this information to some operation center. So our application starts operating according to the received alert. The other goals of this work was propose a traffic light optimization approach for emergency vehicles, reduce the waiting time for emergency vehicles on the roads, and finally reduce the impact of the emergency alert event. Now I will present the context scenario. This figure represents the operation scenario of the proposed approach. As we can see, the city can be mapped by a specific risk zone with different severity levels. We have a neutral risk zone where minus occurrence can happen over time. The region with factors has a high risk of fire, impacting of its risk and relevance of the eventually issued alarms. As we can see, two events of interest happening at the same time and are detected in different zones, generating two different emergency reports. So, after its reports, the respective EPU, the Event Process Unit, receives the alarm and processes the information and transmits it to Operation Center, with each turn start the automatic vehicle dispatching process. There is a center operation with the emergency vehicles are dispatching when the central system receives an emergency alarm generated by the Emergency Process Unit. So if you have curiosity about these elements of these figures, we can see my paper for it. The proposed approach. In this figure is presented the logical flow of the proposed approaches. When an emergency alarm is received and properly processed, the specific vehicles are automatically assigned and dispatched to the location of the report emergency. After it, the emergency vehicle sends a message to the device on the road. It's on to start the traffic light optimization process. So, about the dispatching emergency vehicles approach, the first one is sent emergency vehicles when an emergency alarm is triggered. Due to the scope limitation and the great number of challenges to be handled in this research area, this work was concerned only 3 major groups. There are the incidents considered on this third scope are fire incidents. It's any type of critical events that is generated or may produce fire. This is very common in cities demanding an immediate response of a fire brigade. Health emergencies are some critical situations that may put people in danger, demand the dispersing of ambulance to the affected area. And finally, policy-related incidents such as urban violence, car accidents, public disturbance, we demand the quickly actions by the policy. So, which will be usually implemented by dispersing of police cars. Well, about the optimization traffic light approach, when some type of vehicles goes onto the road, each forwards broadcast message to all road nodes, which will be other vehicles or one or more RSU. What RSU are? Roadside unity that are implemented in a VNet context. Such message presents a geolocation, the type of vehicles, whether it is on operation or not, the vehicle's route, and some metadata that are important to receivers. So this process can be seen here. About the simulation results. This paper made use of software simulation for the practical application of the proposed approach to the complexity of carrying out real experiments. These simulations were employed in a coordinated and integrated manner to carry out the experiments in the defined urban scenario. SUMO is a simulator urban mobility, is a simple road traffic simulator package. OmniNet++ is an open source network simulation environment based on discrete events that allow the modeling and experimentation of communication network. And finally, VANS is an open source simulation environment that allows the exchange between the V2V and V2I approach communications. The VANS is used to integrate the SUMO and OmniNet++ working as an interface application through the trace-I with Python language. The map chosen for the simulation was one of the center of the city of Campinas because the authors already had previous knowledge of how the traffic in the region worked. As can be seen, each RSU controls a traffic light. Here are many traffic lights to be controlled in this road, in this city map. There are predefined roads to evaluate the proposed approach. We can see 2 roads, with the road starts in the red circle and ends in the green circles. We have here the road 1 and the road 2, predefined because the SUMO needs to know previously the roads for simulation. The table presents the parameters and settings employed in the simulation. Two categories of vehicles were included in this scenario: passenger vehicles and emergency vehicles. We have communication, standard communication of the SUMO, communication standard IEEE 802.11p. The broadcast interval is the interval at which messages are sent by emergency vehicles to the other nodes of the simulation. We setting it in 2 seconds, and the warning EV emergency vehicle distance was 200 meters. It's determines the minimum distance between the EV and the RSU that will free up the flow in the traffic light optimization. This figure results, this first result showed the CO2 consumption of the emergency vehicles in the distinguished scenarios. We have here, we have the true distinguished scenario. With optimization is a blue, and without optimization is the orange color. There are the another result. This figure shows the total time spent by the vehicle, the emergency vehicle during the simulation. There is a reduction of approximately 39 seconds between the scenario with and without optimization approach. The correlation between both figures happens because the less time the vehicles is on the road, fewer CO2 is emitted. And finally, our proposed system proved to be capable of identifying an emergency alarm and quickly distributing emergency vehicles to the location of the detected emergencies. And as future works, we will explore other applications in the ITS domain, processing notice settings and real-time data. We will to implement route suggestion algorithms, and finally to explore more efficient algorithms for automatic vehicles allocation. So thank you for your attention, and I'm open to questions.
Thank you, Elivelton, for your presentation. Do we have questions from the audience? So we have a question from Flavia Maristella. Well, it's for interesting work. Actually, you have to deal with several challenges. Do you consider different criticalities in the incidents you consider as your main targets? For example, is there any difference when you consider an accident with human life or a fire accident?
Hello, everyone. Good morning. Flavia, thanks for your question. We don't have a distinguish between the human or fire accident. All of scenarios in the urban, critical scenarios in the urban context are considered about our approach. At least human life or fire accident or leaky in the city and in other critical situations.
Okay. Do we have further questions? I have a question, a quick question about your flowchart. You presented a flowchart of the traffic light operation in the presence of emergency vehicles, and you check if all criteria are met. And I was thinking, what are these criteria that you are checking?
Thank you for the question, Gabriel. Basically, our main criteria is if the emergency vehicles is next to the RSU. If the minimal distance is set in the scenario, how I show it is in the table, in the setting table. If the vehicle was 200 meters next to the scenario, it's the main criteria of the algorithm. If the criteria is met, the RSU free up the flow, and to the emergency vehicle pass faster in this road.
Okay, and what kind of sensors are expected to be used to measure this distance?
Sorry?
What kind of sensors are you expecting to use to measure this distance?
Well, we use a simulator scenario. It's not a specific sensors. We use a simple identifier, a simple sensor that identifies the message based on the VANET context. The sensor needs to receive information and do something based on this information. So it's not I don't have a specific, for example, a Raspberry 3.
No, I don't mean at that level, but I was maybe do you think it will be like GPS based?
Yeah.
Or it will be.
Actually, the message sender has the metadata, which contains the GPS, the location location information, and the vehicle type, if the vehicle is in operation or not. The metadata is already has the information to flow to the sensors in the smart city scenarios.
Okay, thank you.
Because
so, if we do not have any questions left from the audience, we can move to the next paper. So the next paper is entitled Implementing Object Tracking for Seating Quality on Android Devices, and it will be presented by Lucas Mulling from the Western State University of Paraná.
Hi, my name is Lucas Eduardo Fischer Mulling, and our paper is titled Implementing Object Tracking for Seating Quality on Android Devices, with authors me and Professor Márcio Sergio Amado, both from Western State University of Paraná, Cascavel, Brazil. Introduction. The seating quality is crucial to achieve the expected productivity, since the occurrence of duplicates creates a resource conflict between plants, leading to insufficient development of both plants, and a failure or miss leads to insufficient use of the productive area. Seeding quality consists in how well a given distribution of seeds approximates to the ideal distance between each pair of individuals of a determinate crop. The ideal distance is called XREF. Distances less than 0.5 XREF are called doubles. Distances higher than 1.5 XREF are called false or misses. Three main statistics are relevant for determining the quality of the distribution: the percentage of duplicates, the percentage of misses, and the coefficient of variation. With these measurements, we can establish how good the distribution is. For example, given a distribution with a high percentage of doubles and a low coefficient of variation, we can establish that the machinery seeded was calibrated with a wrong XREF. The main motivation behind the software is to automate the process of gathering statistics for the seed distribution done by the LAMAP laboratory of the Western State University of Paraná. This process is currently done manually and prone to human error. As shown in Figure 1, the seeds are laid in a bed of sand with the measuring tape placed parallel to the seeds. Then measurements are taken. Requirements: The main requirements are automated measurement of seed quality. The application must provide feedback to the user in real time. The application must allow the calibration of different seed types. And the application must generate the relevant statistics and display them to the user. Implementation. Figure 2 shows the steps taken by the software for tracking and seed quality measurement. First, we extract the position of each seed from the image. Then, each seed is tracked using a unique ID. The distance between the pair of seeds is then stored. If the process is done, the results are displayed to the user. If not, the process repeats. Implementation feature extraction. The first step is to pre-process the images of the video stream coming from a camera or a recorded video, followed by the extraction of the position of each seed. Each image contains a seed distribution with seeds arranged in a line, where the arrangement can be vertical or horizontal, depending on the camera orientation. To allow flexible input of different seeds, the method for extracting each object from the background is based on the color of the object. Using an upper and lower interval in the HSV color format, a binarization is performed. The lower and upper HSV color intervals are calibrated by the user. The result is a binary image in which the seeds appear as white dots on the black background, as shown here in Figure 3. For this process, the OpenCV library was used. From the binary image, the position of each seed is extracted and converted into a bounding box. The bounding box of an object is the smallest rectangle that includes all features of the object, and is represented in memory as x1, y1, x2, y2, where the pair x1, y1 corresponds to the upper left corner, and the pair x2, y2 corresponds to the lower right of the bounding box. Implementation tracking. To track each seed, we use the sort algorithm. The main components of the sort algorithm are the Kalman filter and the Hungarian algorithm. The Kalman filter predicts the next state of a given object based on its position and the velocity of each axis. Sort uses the intersection of a union method to determine a weight for each tracker and detection for the cross matrix of the Hungarian algorithm. By calculating the weights of each tracker and detection, an optimal assignment is achieved using the Hungarian algorithm. In this case, by assigning the trackers and detections with a higher value of intersection of a union, the result of the Hungarian algorithm is the assignment of a detection to a tracker. The result is then used to correct the filter and update positions, scale, and velocities in the model. To better fit the sort algorithm to our problem, 3 modifications were made. The first one is to change the weight function, since the intersection over a union method does not allow for overshooting of the Kalman filter prediction. As shown here in Figure 4, the white dot represents the seed. The green rectangle represents the bounding box of the detection, and the red rectangle represents the bounding box of the prediction of the Kalman filter. In this case, the intersection of your unit would be 0, causing the tracker to lose association. Another change was the use of a different model for the Kalman filter. The original model is described as a tuple U, V, R, and S, where U and V are the coordinates of the center of the object's bounding box. S is the area of the detection's bounding box, and R is the aspect ratio of the bounding box. The new Kalman filter model only uses U and V, the center of the object's bounding box. Another modification made was to return as the tracker result the association, not the prediction of the Kalman filter. Methodology. Testing of different weight estimators and Kalman filter models was made using a Python prototype, using a recording of a seed distribution done by the LAMAP laboratory. 3 different weight estimators were tested: the Manhattan distance, the Euclidean distance, and a hybrid equation, shown here in equation 4, which primarily uses the intersection of a union to compute the weight value for the Hungarian algorithm, and allows for crossing of the detection and prediction boundaries. The equation works by calculating the intersection of a union of both bounding boxes. If the result is greater than or equal to an error E, the intersection over a union result is used. Otherwise, the inverse of the Euclidean distance times a factor f is used. This provides some leeway when the bounding box of the detection and the bounding box of the prediction do not overlap. To test the accuracy of our solution in measuring distances in real time directly on the Android device, a uniform distribution of 10 seeds was made. The tests were performed with black bean seeds placed in a row on a background of wax paper to simulate real-world conditions, with each seed spaced 10 cm apart, meaning that xref is equal to 10. Testing was performed by moving the smartphone from left to right after calibrating the software. The test was performed with the smartphone at an approximate distance of 20 centimeters from the ground. The second test consists of a non-uniform distribution of 10 seeds, shown here in figure 6. The distribution contains 3 seeds whose distance is less than 0.5 xref, meaning that they are doubles, and 2 distances that are greater than 1.5 xref, meaning that they are misses. All of the tests were performed using a smartphone LG K12 Plus with Android version 9. Results. Table 1 shows the results obtained with each of the 3 variants of the Kalman filter and the distance estimator. The hybrid model performed the worst of the 3 in the tests. Both variants using the Euclidean and Manhattan distance performed equally well. All of the methods failed to extract the ideal distribution from the sample. This was likely due to the conditions of the video, which are particularly difficult for the tracker, as the jump cut forward in the video causes the tracker to lose the association. In Table 2, we can see the results obtained with the tracker compared to the ideal measurements of each distribution. For the uniform distribution, 9 of the 9 distances were measured correctly, with a coefficient of variation only slightly different from the ideal result. For the non-uniform distribution, the number of measured distances was higher than the actual number of seed pairs. The number measured by the software was 11, while the ideal value was 9. This was caused by the light reflection generated by the black beans, which in turn can lead to false positive detections. The percentage of doubles and misses was close to the ideal value. Performance of the application was evaluated in terms of frames per second. The result showed an average of 27 frames per second with 5 seeds, seen here in Figure 8, Scenario 8, and 26 frames per second with 10 seeds in focus, shown here in Figure 8, Scenario B. Profiling was performed using Android Studio's built-in tools to collect a baseline memory consumption, which was about 100 megabytes. Most of the performance of this software is tied to the feature extraction phase of the application. Conclusion and future work. The application developed shows the possibility of using OpenCV and the SWORD algorithm for developing object tracking solutions on smartphones. The application achieved a frame rate of 27 frames per second, running directly on a real smartphone. The OpenCV API proves to be a viable tool for developing image processing solutions on mobile devices. However, there are still problems that make consolidation difficult. One of the issues we encountered during the development was a bug related to the portrait orientation of the camera on Android. It is worth noting that the bug was reported in July of 2015, and at this present time, it is still not fixed. To fix the issue, a change was made to the camera bridge view base class that results in a significant performance loss of about 3 to 4 frames per second. The results obtained with the adaptive tracking algorithm show that it can track the seeds located in the scene and label them accordingly. The inaccuracies obtained with the actual data are due to the object detection phase, which failed to eliminate the noise that led to the detection of phantom seeds. Based on the obtained results, a more robust method for extracting seeds from the image will be investigated in future work. Acknowledgements to the Fundação Araucária for providing funding for the project and to the LAMAP laboratory.
Thank you, Lucas, for your presentation. Do we have any questions? Well, I have some questions. When the user is ready to use the application you have developed, is it necessary to have some kind of reference object so that to perform some kind of calibration, or it's simply point and click and take a picture and the algorithm will measure distances based on that only?
Hi, can you hear me?
Right. Yes.
So the user will first calibrate the color of the seed, and then he will input the XRF distance, which is the ideal distance of that given seed distribution. Then he'll calibrate the distance, the ideal distance, usually a known distance, and then he can simply slide the smartphone over the distribution, and all the measurements are done automatically.
Okay, and how sensitive is the results, or how sensitive are the results to, like, how far the user holds the cell phone? Let's say, does the user need to have a very steady arm to move the cell phone through the seeds, or, I mean, if the user holds it closer or further away from the seeds, that will affect the results, I assume.
Yes, they affect the results, but the effect is very, very minimal.
Okay.
A couple of millimeters. And we do have measurements implemented to try and fix that.
Okay.
And in certain smartphones that have dual cameras, you can also use them to correct the distance.
Oh, okay. Okay, that's interesting.
But we don't have that implemented yet.
Okay. Do we have any questions? No? So if we don't have any other questions, we can move on to the last paper of this session, which is an open source custom k-means generator for AWS Cloud FPGA accelerators, and it will be presented by Lucas da Silva from the Federal University of Viçosa.
Hi, I'm Lucas, the first author of the paper, an open source custom k-means generator for AWS Cloud FPGA accelerator. The other authors of the paper are Michael Kaneski, Jerome Penha, Wesley Carvalho, and the professors Giovanni Comarella, José Augusto Nassif, and Ricardo Ferreira. And now I am going to present the paper. The presentation will follow this summary. First, I will introduce k-means and show some of the challenges to implement a k-means accelerator. Then I will introduce you to AWS Accelerated Compute Platform with FPGA that you use. Next, I will present the proposed accelerator. And finally, I will present the results and conclude the presentation. K-means is an algorithm of unsupervised classification. The algorithm learns to classify based on the distance that given a point is from the center of the set of points. These centers we call the centroids a cluster. The number of centroids is determined by the user and is an input to the algorithm. In this example, you can see visually that this dataset has two groups. That is, we need two centroids to classify the other points. So, the algorithm starts with two centroids random, and based on the distance between them and the dataset points, it performs an update on the centroids. So, they get more and more to the center of the two groups, and this occurs the algorithm converge and finish the execution. For the implementation of the k-means, we use the Euclidean distance, where the objective is to minimize to average of the distance of all the centered points. However, to simplify the implementation of the accelerator circuit, we minimize the distance to the square, so we don't need to calculate the square root. So the two challenges to develop a k-means accelerator that has a good performance are: first, it has good throughput in reading the points. Since we will have to classify all the dataset points, this is a memory limitation issue, especially when the number of the centroids is small. Since for each reading, we need to perform a few operations on the data. And second, for cases where we have a large number of centroids, we have the computation limitation of all these points, but we have a better reuse of the data, since we are going to perform more computation on each point. To solve these problems in accelerator, it needs to have an efficient interface for reading and writing to memory, and it has multiple processing units. Thinking about these two challenges, we implemented our accelerator in the form of the data flow, where the number of operations we perform to each entry point is around 3kn. This graph describes the operation performed to classify each point, where the points are read from memory and it's passed through the data flow in pipeline way. We designed our accelerator to run on AWS Accelerator Compute Platform that has an FPGA built into the system. This platform is available on AWS Cloud, where anyone can rent and use it. The platform consists of 2.3 GHz Xeon processor with 64 GB of memory and an Xilinx FPGA UltraScale Plus. The FPGA also has 64 GB of dedicated memory. The FPGA is divided into ports. The shell, which is an area dedicated to AWS, and it is responsible for controlling the user kernel execution and the interface with the memory. The user dedicated part is called custom logic and is where the user kernel is mapped. It is possible to add several memory read interfaces to the user kernel through the X protocol, but the bus has a limitation of 512 bits, and the ideal is to use only 4 axes, one for the memory channel. Programming FPGA is a challenge because you need to have knowledge of the hardware language to get good performance. To get around this problem and allow users with no hardware experience can use our accelerator, we developed a parameterizable generator where the user just enters the number of centers and the number of the dimensions of the dataset and all the necessary framework to run k-means in the cloud of AWS is generated. Our generator will replicate processing units based on the centroid number and the dimension, using the maximum bandwidth of the AX interface, which is 512 bits, in order to read 32 points of 16 bits in parallel and pass its inputs to the unit process. Each process unit has 16 replicas of the k-means data flow, where these points are processed. To evaluate the performance of our accelerator, we use the 1990 US sensor datasets and generate accelerator with different amounts of centroids and dimensions. We vary the number of centroids from 2 to 16 and 4 dimensions from 2 to 32 in power of 2. We also made a comparison with other work that has the same accelerator but on HARP v2. That is a research platform. In this chart, we have the iteration time of each accelerator run on the AWS platform. We can note that time only increases when the number of the dimensions increases. This is explained by the increase in the amount of data when it increases the number of the dimensions. The same results don't happen when you increase the number of centroids, because the calculations are done in parallel. This is, when the centroids increase, the amount of data remains the same. In this chart, we present the performance of the accelerator in operations per second. In this case, we have an increase in performance when we increase the amount of centroids. This explains because the number of operations increases when we increase the number of centroids, but the amount of data is the same. Accelerator with the number of different centroids, that is, for large centroids values, we have more data reuse, provides more giga operations per second. As a conclusion, we present a complete end-to-end cloud FPGA accelerator. The entire project is open source and available on GitHub. Our accelerator on AWS is quite fast as the version present in past work on HARP v2. As future work, we are going to implement the complete k-means on the accelerator. This was my presentation. Here is our contact and the code repository. I would like to thank USV and the other development agents. Thank you for your attention, and I am open to questions.
Thank you, Lucas, for your presentation. Do we have questions? So, if I understood correctly, your work is it's basically generating a parameterizable RTL code for the k-means accelerator, right?
Right.
And have you considered comparing your performance results with let's say, an accelerator generated with high-level synthesis from a C code or an OpenCL code, for example?
Yes, we thought about this, but we don't have acknowledged in GLS, and we try make the simple code, and the results is very bad because GLS is very you have put pragmas to optimizing your code, but I don't have this acknowledgement, and for this we don't put the results in the paper.
Okay. And you mentioned this HARP v2 solution. It's from other authors then, if I understood correctly.
You can repeat because
the other solution you have compared, the HARP v2. It was developed by other authors, but it's also based on an FPGA. Do you know what was the development tool flow that they have used? They have used also RTL code, or have they used high-level synthesis?
In the HARP, the work is from our group, and we have the same code.
Okay. So it's okay. Okay. And you mentioned at the end of your presentation that your next goal would be to have a complete K-means accelerator running on the FPGA. And my question is, what are the main steps that are still missing to have a complete accelerator, and what are the challenges that you expect to find when trying to do that?
And this accelerator, we just put the classification step, and the update centroids was be in CPU.
Okay.
And to translate this for RTL, I have some difficulty because we have make division. That's the operation is very difficult in FPGA, and have updated the centroids, and I try the logic of the accelerator, have in the start of the algorithm is the reading the memory and update the memory in the same in the hardware. It's very it's more difficult to make this, but we try create the accelerator and try in the FPGA, but in progress work.
Okay. And your current implementation, is it operating? It's in fixed point, or is it floating point?
We use intelligent and 16 bits.
Okay. Yeah, that makes a huge difference when talking about how hard would it be to have a divider in hardware. But yeah, it's not very efficient in FPGAs, regardless whether it's fixed or floating point. At least from my previous experience. Do we have any other questions? No? If not, then we can conclude this session. I would like to thank all the attendants, thank everyone for being here. I would also like to thank the authors for being here, for answering all the questions. And I would also like to thank Leonardo for the tech support, and hope to see you at the next sessions.